Okay, this is Unit 2. We're going to be focusing on functions and graphs here. A lot of different functions and graphs of those functions is the focus. This first part, we're going to be looking at basics of functions and their graphs. So we have some objectives up here at the top. Determine whether a relation is a function. So we have to know what a function is first. Then evaluate a function given ordered pairs, the graph, or an equation. So a couple different ways to evaluate functions there. Using the vertical line test to determine if a graph represents a function. Identify domain and range of a function, and then intercepts of a function. So we have a lot going on in this first part here. Let's take a look at the idea of a relation first. This asks us to graph a relationship between the number of nickels and the value of those nickels. So over here, this x is going to represent the number of nickels. Y will represent the value of those nickels. So I'm going to think about, I can't really, on my x-axis here, I have -1, but I can't really have -1 nickels, where x represents the number of nickels. But I could have 0 nickels, and the value of that would be 0. If I have 1 nickel, the value of that is 5. If I have 2 nickels, the value is 10. If this, I guess I should be a little more specific here. We should say in cents, right? Otherwise it doesn't work on our graph very well. 3 nickels are 15 cents. 4 nickels are 20 cents. 5 nickels, I'm just plotting points here, right? 5 nickels, 25 cents. 6 nickels are 30 cents. So a good question for you here is, do I want to connect the dots? The answer is no, because I can't have, when I connect to the dots, that implies that I want to have a point in the middle there, like that, which would be like having half a nickel. If I have half a nickel, it certainly doesn't have value 2.5 cents, right? You can't trade in half a nickel for 2.5 cents worth of a cheeseburger. So I definitely do not want those points in the middle there. I only want the points on these integer values for x, in fact, natural number values for x. Integers include negatives, and I can't have a negative number of nickels either. The question here says, write an equation to express the relationship between the number of nickels and the value of those nickels. Well, if I'm using y to represent the value of those nickels, what is the relationship I have here? The value is 5 times the number of nickels that I have, right? If I have x equals 1, y is 5, right? This is 5 here. When x equals 2, y is that 10. When x equals 3, y is this 15, and so on. Okay? And so that's our relationship between the number of nickels and the value of those nickels. We're going to start talking about this more mathematically and less in this sort of real application. In an equation, the variable that depends on the value of the other variable is called the dependent variable. The other variable is the independent variable, the one that doesn't depend on it. The set of possible values of the independent variable is called the domain. The set of possible values of the dependent variable is called the range. Let's find each of these things in the nickel example. So we want to know what is our independent variable and our dependent variable. First of all, so the determine which variable is dependent and which is independent. My 2 variables here are number of nickels and value of the nickels, right? Which one of those depends on which? Well, the value that I have in my hand depends on how many nickels are there, right? So the value is what we are going to call the dependent variable, and then the number of nickels is my independent variable. These, oftentimes I find it easier to find the dependent variable before the independent variable. Which one depends on which? When we're talking about these, we want to talk also about the domain and the range. It asks us also to find the domain and range. Domain is the possible values of the independent variable. So that corresponds to the number of nickels. We talked about this a little bit. You can't have a negative number of nickels. You can't have half a nickel. So we're talking about this set, 0, 1, 2, 3, and so on. That's called, yikes, that's not right. That's not the natural numbers. That's the whole numbers because it includes 0. So we would call this the whole numbers. Sometimes you'll see it with like a bolded W for the whole numbers. As far as the range, that is in reference to the possible values of the dependent variable. In this case, well, we could have a value of 0. When we have 1 nickel, we have a value of 5 cents. And we have 2, 10, and so on. There's not a good, nice name for this, so we're just going to write it as that set is my range. Can't be anything else other than those multiples of 5. Okay? We could write it in what's called set builder notation and give some words to it, but we'll just leave it like that for now. This question also asks us, so we did this here in green. We did this part in blue. Let's go ahead and pick a third color here. Let's go orange to answer this question. Determine at least 3 ordered pairs that satisfy the equation. When we have variables like this, we list the independent variable first, the dependent variable second in our ordered pairs. So we had 0, 0, certainly, right? When x is 0, y was 0. We also had 1, 5. We also could have had 10, 50. That was not on our graph, right? But it still satisfies the equation. These dots in our domain and range tell us that goes on forever and ever. So we could certainly have that as an ordered pair satisfying this equation. All right, so this is kind of talking about a relationship between 2 variables, right? What we want to know is what specifically is a function. That is a specific type of a relation, and that's what we want to talk about for the rest of this unit, really, is functions. Our definition of a function is a relation in which each element of the domain corresponds to exactly one and only one element of the range. I have some pictures here because I want you to think of a function almost like a box. You have an input into it. That's what the domain values are. They're inputs in here, and then you get something out of it. And this function box does something to that number that you input, and then it spits something else out. So maybe you have a function box that adds 3 and doubles the number. Okay? And so if we put 2 in here, we add 3 to that, we get 5, and then we double the number, our output would be 10. What I have over here on the right side is sort of showing this relationship where this is our domain, because that's our input values, and this is our range. And we connect that 2 to that 10. An important idea of a function is that if I put 2 in, and I add 3 to it, and then I double that number, I am only going to get 10 out if we do it in that order, right? So maybe we should be more specific here, and then doubles that number, just to be very clear about what we mean. So if I put in, let's suppose I put in 6. 6 goes in, I add 3 to it, I get 9. I double that number, out comes 18. So over here, 6 would go to 18 and would only go to 18. It would never go to any other number. Okay? No, so yeah, so we get that. We could write an actual equation to describe this, right? If these are my x values and these are my y values, well, my input x gets 3 added to it, and then we double that whole thing, and that gives me out a y value. That if I plug these numbers in for x, I will get the y values over here in the range. So that's the kind of relationship we're talking about. An important idea here is that we are only talking about getting, when you put one thing in, you get one thing out. That doesn't mean that you can't put 2 different things in and get the same thing out. Let me show you what I mean. Whoa, what's happening here? Let's go back up here. All right. Moly. Okay. For example, let's suppose you had an input, whatever that is, and you want to square the number. That's the function. That's what you want to have happen to that number. So let's suppose we input in 2. In comes the 2, out comes 4, right? When you square it. So over here you get 2 goes to 4. Or if you input 6, out comes 36. So 6 goes to 36. We put one number in, we get one number out. All right, well, let's suppose now we put in a -2. Oh, I square that number. Oh, I get 4 again, right? So that means when I put -2 over here, I'm not going to repeat that 4. I'm just going to draw an arrow connecting to that 4. Does that make that not a function? Well, our definition says each element of the domain, so whatever element of the domain I have, corresponds to exactly one element of the range. Meaning, if I have a number over here in the domain, when I square it, do I get 2 different possibilities to come out of my function box for one thing going in? No, I don't. I had 2 going in, going to one thing coming out, but that doesn't violate the definition of a function. What violates the definition of a function is you put one thing in and you get 2 or more out. Okay? So that's what we need to be careful of. Let me give you another example. I didn't leave the space here. Well, maybe we can do it down here because we'll have an example down there. Is this nickel to value of the nickel relation a function? If we do it with the circles, where this is the domain and this is the range, over here I have 0, 1, 2, 3, and so on, right? Over here I have 0, 5, 10, 15. 0 goes to 0, 1 goes to 5, 2 goes to 10, and so on, right? This is a function. Just like both of these up here are functions. This up here was also a function. This one we didn't write the equation, but it was the equation y equals x squared. put in a value in for x, you square that number, you get the y value out. One thing I want you to think about, I really want you to think about the definition of a function here and not just the numbers and how they correspond. For any number of nickels that I have, do I have two different values of those nickels? If the answer to that is no, it is a function, okay? So if I have a certain number of nickels in my hand, it is always worth or has the same value as far as it is its coin value, right? Not, maybe of some rare nickel or whatever. We're not talking about that. We're saying a nickel is worth 5 cents that you can go spend at the store, right? However many nickels you have, the value of that is always that number multiplied by 5. Okay, so you have one output for that input of how many nickels you have. Let's take a look here. Which of the following relations are functions? So this is just a bunch of ordered pairs. Remember, all of these relationships between independent variable and dependent variable kind of boil down to ordered pairs. Up here, we could write this ordered pair here as the ordered pair 2, 4. Or we could write this one as 6, 36. The last one there we could write as -2, 4. Independent variable first, right? That's all that we have down here is we just have these 4 ordered pairs, okay? We want to know for every input, do we have a unique output? So I input 3, I get out 2. I input 6, I get out -1. I input 5, I get out 0. I input 0, I get out 7. Range values, domain values. No problems there, right? Okay. What about this one? Here for my domain, I have 2 going to a range value of 4. I have -1 going to a range value of 3. I have 4 going to a range value of 1. And oh wait, I have 2 again going to 5. This one we said was okay. It's a function. This is not a function because I have one input, this 2, going to 2 different output values, 2 different y values. Okay. Let's talk about this from a graphical perspective. The vertical line test can help us with this. Let's talk about why. What the vertical line test says is if a vertical line can be drawn so that it intersects a graph at more than one point, then the graph does not represent a function. Use the vertical line test to determine whether the following graphs represent functions. Look at this cute little heart here. Isn't that fun? Okay, here's what this is saying. If we can draw a vertical line that will cross... What's going on here? I have no idea why this is scrolling all the way down. I'm sorry. Back to our heart. Where's our heart? You can see we have a lot of material to get through in this unit, huh? Okay, here we go. If we can draw a vertical line that intersects the graph at more than one point, then it is not a function. So for example, here, I draw this vertical line. It intersects the graph at 2 different spots. That tells me immediately it is not a function. Why? That is saying for this particular x value, whatever that number is, I have 2 different y values that it is corresponding to. That is not a function. Okay? over here, no matter what vertical line I draw, it only hits the graph at one spot. That means each x value that I could draw a line at, no matter what x value I draw a line at, any of these numbers, they don't have to be integers, any of those numbers that I draw a vertical line at, I only get one y value on the graph. For this one, it's that point. For this one, it's that y value. This one, y value. And so this is indeed a function. Okay? These are some fun equations that we have here. This one I think is kind of super fun, right? That's a pretty wacky equation we have there to get that heart. Okay, function notation. Most of the time we are going to see functions, we are going to see them defined by equations. Y equals 2x is a function because, well, let's talk about y. Every input gives a single output. Whatever you put in for x, it's sort of implied, by the way, if you have a relationship between x and y, unless it states otherwise, that x is the independent variable, y is the dependent variable. No matter what you put in for x, that number, y is going to be double that. So if you put in 10 for x, y is going to be 20. You put in 10 for x, you are only going to get 20. You are not going to get a bunch of other things. Okay? Here, however, is not y as a function of x because we can find two y values for a single x value. So for example, if x equals 9, y could be 3 or y could be negative 3. And so because you have one x value going to two y values, this is not a function. I had a student tell me once that he remembered it by saying you can have multiple dogs in the same doghouse, but you can't have one dog in multiple dog houses. I don't know. That helps you. That's how he remembered it. So if that helps you, go for it. Okay, we use some notation for functions to help us sort of minimize our work and make things tied up in a nice, neat little package. We use this notation right here, and we say f of x. That's the language that we use for that. So for example, this one that we said was an equation, was a function, y equals 2x is an equation, is a function. It can also be written as f of x equals 2x. That doesn't mean f times x, it's f of x. And what that means is that I can input whatever value I want in for x, and the output of that is that dependent variable value. So we're kind of replacing the y with the function notation. This particular function has the name f, but it could have a different name. It could have the name T if it's representing temperature, or it could have the name P if it's representing pressure in a physics problem. Okay, so it's just whatever name you give it, just like I have a name or you have a name. That's just the name of the function. The x here is kind of like that dummy variable that we're using to represent values of the domain. Let me give you an example of how we're going to use this. Let's suppose we have this function, f of x equals 3x squared minus 5x plus 1. Remember, that's kind of like the y, right? But what this is saying is everywhere I see an x, that's my x value, right? The x is here, is replaced by 4. I'm going to replace the x with 4. So that gives us 3 times 16 minus 20 plus 1 will be 48 minus 20 plus 1. That's 28 plus 1, which is 29. Okay? Everywhere, when you see this notation, it means replace the x with 4. Whatever's inside there gets replaced by, or x gets replaced by that. So here I have f of smiley face. Well, that means 3 times smiley face squared minus 5 times smiley face plus 1. Obviously, we can't simplify that. The point here is to let you know that whatever's inside that function notation replaces the independent variable in the function. So in this case, the x. We're going to do a few more of these just to practice. G of negative 3, where g of t is 1 over t plus 4. The independent variable here is t. So g of negative 3 replaces the t, and you get 1 over 1 or 1. So we would say g of negative 3 equals 1. This represents the ordered pair, if we were to try to graph this, of negative 3, 1. Negative 3 was my t value, my independent variable value. The output of the function, when it ran through this function, was 1. No matter what I put in for t, that's always going to simplify down to a single number. So that's why this is a function. Same thing here. I put a value in for x. No matter what that number is, it's going to simplify down to a single number. So this is a function. Absolute value of 10 is 10. When you double that, you get 20. So h of 6 is 20. Ordered pair, 6, 20 would be on the graph of this function h of x. One more. This one's worded a little bit differently. It says let g of x equal the absolute value of x minus 8. Find x if g of x is equal to 3. Here I'm asking you to find the x. I did not give you an x value. Notice the difference. Up here, I gave you the 6 to represent the x, right? It's inside that h notation. Here, I have not given you the input value. I have given you the output value. Remember, this is like saying y equals 3, because that function notation and y are kind of interchangeable. That means I'm going to replace g of x, the whole thing, with 3. And I get 3 equals the absolute value of x minus 8. It says find x. This one, you probably have seen how to solve this using techniques from your previous classes. That should be a prerequisite for this. But if you haven't, let's just think about what x values make this true. Well, the absolute value of 3 will equal 3. So if x is 11, I get a true statement, right? That one's usually the one that students see pretty easily. There's actually another solution here. When x equals 5, you get a true statement, because x equaling 5 gives you the absolute value of negative 3 on the right side here. The absolute value of negative 3 is equal to 3. The official way to solve this absolute value equation is that x minus 8 equals 3 or x minus 8 equals negative 3, and then solve both of those, add 8 to both sides, and you get these two solutions if you can't see it from sort of trial and error. Okay, we have two solutions here. Does that make this not a function? This x equals 11 corresponds to the ordered pair 11, 3. 11 is the x value, 3 is the y value, so the second coordinate in the ordered pair. Same thing for that x equals 5. this is still a function. When I plug in any x value, I still only get one value out. Okay, I plug in 5, I get 3 and only 3. I plug in 11, I get 3 and only 3. That is okay. The problem is if I plug in one x value and get 2 different y values from it. Okay, that's where we run into problems. This is still a function. Okay. Oh boy. Okay, we're going to look at a few more examples, then we're going to stop this video. We're getting pretty long here. So we're going to do this last couple of examples here on function, using function notation. Celsius temperature, C, is a function of the Fahrenheit temperature. We have these two different temperature scales, right? We have more than that, but we do have these two. There's a relationship between them. This equation, this C of F, that doesn't mean C times F, it means C of F, shows you the relationship between them. Determine the Celsius temperature that corresponds to 451 degrees Fahrenheit. That means when F is 451, what is C? That's what you want to know. Notationally, we replace the F with 451 degrees. I picked that because the book Fahrenheit 451, that's the temperature at which paper burns, right? So, interesting book if you haven't read it. All right, 451 minus 32, following order of operations, is 419. And when we multiply that by 5 and divide by 9, we get approximately, let's do an approximation here, 232.78 degrees. That's Celsius. That's the output. The input here, we put in a Fahrenheit temperature. We take out a Celsius temperature. And that's our answer. If we wanted to give an exact answer, just depending upon the system you're looking in, it may not, it may want you to leave it as a fraction. So you would leave it as 2,095 over 9 if it was looking for an exact answer instead of the approximation. On a problem like this, I would think that it wouldn't, but in case it does, make sure you're very careful about what you're reading when you're entering your homework in the system, because it will be specific about whether it wants you to round or it wants you to give an exact answer. Okay, we saw this function before. We said that it was a function. Notice the x coordinate is not repeated to two different y values. F, oh shoot, I missed something here. This should say let f equal that. That's our function. F of 6 means when you input 6, what do you get out? This is my input, -1 is my output from that ordered pair. This one is saying what is x if f of x equals 7, excuse me. That's your y value. What is x? That's what this question is asking. Remember, this notation is kind of replacing the y. And so that answer is 0, because f of 0 equals 7 from that last ordered pair there. Okay. When we come back, we are going to look at graphs of functions and use some and talk more about how these idea of a function that we have seen relates to graphs. Okay, so look for the next video.